Okay, so this first question on this little study guide says ammonia can decompose into its elements according to this equation. We're given a Kp value at 700 Kelvin, and it's 0.016. So right off the bat, I will note that this is a small K value, so this is going to be reactant favored. Reactant favored. Okay, so part A, write the expression for Kp for this reaction. Well, we want a Kp. Kp is equal to the partial pressure of the products. So the partial pressure of nitrogen, I'll put in parentheses just for some clarity, times the partial pressure of hydrogen, which has a coefficient of 3, so we'll have a power of 3 here, over the partial pressure of NH3, and that NH3 will be squared since there's a coefficient of 2 out front. So there is the expression for Kp for this reaction. For part B, a reaction vessel initially contains 0.5 atmospheres, so we'll say 0.5 atmospheres of that, with no nitrogen or hydrogen, and it wants to calculate the equilibrium pressure of that NH3. Well, think about an ice chart here. We have 2 NH3 to make nitrogen and 3 hydrogens. Initially, there's 0.5 of the ammonia and no nitrogen and no hydrogen. We know that we are going to gain some nitrogen, and we're going to gain 3 times as much hydrogen, so whatever x is, we'll multiply that one by 3. And we're going to lose some ammonia here. That gives us equilibrium concentrations of the nitrogen of X, of the hydrogen 3X, and of the ammonia 0.5 minus X. Now, if we were to try to plug these values here into our Kp expression, you will notice that this piece right here is going to present this to be a quadratic equation, which you'd have to use the quadratic formula to solve. So that's our clue that we can make our assumption here. And our assumption is that since this Kp is so small, the change in this ammonia here is negligible. So for all intents and purposes, this is still going to be 0.5. So now we can just go through and we can plug these values in to our Kp expression. So let's go ahead and do just that. We'll replace the pressure of the N2 is X. The pressure of the H2 is 3x, and of course that was cubed. The pressure of the NH3 we're going to leave as 0.5 due to our simplifying assumption, and that one was squared. So let's clean this up just a little bit, and we can also plug in our value for Kp, which we know. Let me see if I can get some more room here. Now that's better. We can plug in our Kp value, which was 0.016, 0.016. We can clean this top part up a little bit. This is x times, now be careful, because this cubed is going to the 3 and to the x. So this ends up being 3 cubed, which is 27, and x cubed, which is x cubed, over 0.5 squared is 0.25. So we can clean this up a step further now. X times 27x cubed is 27x to the 4th, divided by 0.25. Multiply both sides by the 0.25. The left side comes out to be 0.004 equals 27x to the 4th. Just keep cleaning this problem up. We'll divide both sides by 27. Plugging that into the calculator. Going to start getting into scientific notation here pretty soon. This is 0.000148 equals x to the 4th. So now we need to take the 4th root of both sides here. I didn't leave myself much room. X to the 4th. We'll take the 4th root of both sides. And x ends up being 0.1103. So let's go back and see what that means for us here. We are trying to find the equilibrium pressure of NH3. Well, originally, the pressure of NH3 was 0.500, but we said it's going to lose some value of x here. Well, that value of x is what we just calculated right here. This is the amount of that NH3 that will be lost. So we just have to subtract 0.1103. So 0.5 minus our answer from the previous problem, and this will give us a ending pressure of 0.3. Let's see how many sig figs we have here with 3 sig figs. So 390 atm. That will be our final pressure of the NH3, or the equilibrium pressure of the NH3. Now, technically, there's probably a valid argument here that this is too big of a difference to be negligible, but in terms of AP Chem, this is going to be a good enough work for it. Okay, so moving on to part C, let's clear this out. Part C, explain whether the total pressure inside the vessel increases, decreases, or stays the same as the equilibrium is approached. Well, consider at the beginning there was 0.5 atmospheres of this, but none of this and none of this. Well, we know this equilibrium, even though it's not going to shift very far to the right, it has to progress to the right. There has to be some of each of these present for equilibrium to exist. So because of that, some of this will be lost to turn into product. We'll take a look at your coefficients. You have 2 moles of gaseous reactant, and that's becoming 4 moles of gaseous product. So it doesn't really matter how much of this side we lose. For every piece of that side we lose, 2 moles are disappearing, but 4 moles of gas are being produced. So because of that, there's guaranteed to be an increase in the gaseous moles here. Well, an increase in the gaseous moles will result in an increase in pressure. As this system moves to the right, it produces more moles of gas, which means the pressure of this vessel must increase. Number 2 talks about solubility equilibria and the common ion effect. We're given an equation here with some lead 2 sulfate. We're given a KSP value, which is tiny. That's to be expected. This lead 2 sulfate is largely insoluble, so we would not expect this to progress to the right to any large extent. So A, calculate the molar solubility of the PbSO4 in pure water. Well, when in doubt, let's write a KSP for this equation. KSP equals the concentration of the lead 2 plus ions times the concentration of the SO4 2 minus ions. Now, we don't know how much of this is going to dissolve, so we can call our lead concentration X. For every 1 lead, there's also 1 sulfate, so we could also call this guy X. We know the KSP value to be 1.6 times 10 to the negative 8th, so we can plug that in right here. 1.6 times 10 to the negative 8th. So we're ending up here with 1.6 times 10 to the negative 8th equals x times x, which is x squared. So we simply have to take the square root of both sides, square root left and right side, and that ends up with me getting x equals 0.00013. Now I want to pause and think about what we just solved for here. We established x to be the concentration of the lead 2 ions, which is fine. Just understand that that means that's the molarity of the lead 2 plus ions. Now that does not technically answer this question as asked. We're looking for the molar solubility of PbSO4. In other words, what molarity of PbSO4 is able to dissolve in water. Luckily, since this is a 1-to-1-to-1 ratio, this 0.00013 molar lead corresponds to 0.00013 molar of the salt from which it came, which is the PbSO4. So because it's a 1-to-1 ratio here and here, these values are the same. Just understand, answering this might not earn you full credit on the test because you technically did not answer the question. We needed the molar solubility of the PbSO4, not necessarily just the lead ion. So let's clear out some of this junk here. I'll leave this number here. We might need it for the next question. And part B says a student dissolves some PbSO4 in a solution that already contains 0.1 molar of Na2SO4. Explain whether the solubility of the PbSO4 increases, decreases, or remains the same compared to pure water. Justify your answer with Le Chatelier's principle. Well, this 0.01 molar Na2SO4 means that there's already 0.10 molar SO4 ions in the solution. Well, think about what Le Chatelier's principle is going to do here then. You already have an increased amount of SO4 of the sulfate ions in the solution. Since there's already a large amount of the product in the solution, this is going to shift this equilibrium to the left. This is the common ion effect. So let's go ahead and answer the question. We know the common ion effect results in a decrease in the solubility of a salt. Decrease, and we could say something along the lines of the SO4 2- is a common ion according to Le Chatelier's principle. The increase in the concentration of the SO4 2- will push this equilibrium, my handwriting's getting bad, I'm sorry, to the left, which is indeed the solid salt, which decreases the solubility of that salt. Very common question. You could even have to calculate what the new concentration would be, or what the new solubility rather would be, and that would be used just with your KSP. We know that this is the lead 2+ ions, and this was the SO4 2- ions. We could calculate a new concentration here of the lead ions by using this 0.1 molar in place right here, because this 0.01 molar is going to be significantly larger, so we can just plug that 0.1 in and solve for a value here, and you will find that that answer will end up being less than our originally calculated answer. Again, that's an example of the common ion effect. Number 3 is also about Le Chatelier's principle, but it kind of takes a different approach with it. We have this equilibrium here. We're told that this reaction is endothermic, so delta H here is greater than 0, or we could say it's positive. It's endothermic. So we could also think that that means that heat is being treated as a reactant, in essence. Heat is flowing into this. They tell us that this complex ion here is pink. So we have this one that is pink in color, while the COCl4 rather ion is blue. So this guy is blue. Predict the color change when the solution is heated. Well, we have to consider this then. Equilibrium is going to shift one way or another when the temperature changes here. When the solution is heated, heat is being added. Heat in this case is a reactant, quote unquote. So think which direction Le Chatelier's principle is going to push this. We're adding heat. That's going to push this equilibrium the opposite direction of that stress. That's going to push this reaction in the forward direction. So thinking what the color change will be, it should become less pink and more blue as this reaction pushes to the product side here. So to answer this question, A, the solution becomes less pink and more blue, and our rationale there is increasing the temperature of an endothermic reaction favors the forward reaction. As we favor this forward reaction, the system should turn more blue and less pink. For part B, a student adds a few drops of concentrated HCl to the equilibrium mixture. Predict what will happen to the intensity of the blue color and why. So this one's a little bit, got to think outside the box here. This HCl is going to break up into hydrogen ions and chlorine ions, or chloride ions rather. So there's going to be more hydrogen ions and more chloride ions than there were. Well, hydrogen's not really part of this equilibrium. However, this chlorine is. We are adding more of this chlorine to the system. So again, Le Chatelier's principle says it's going to reestablish equilibrium to offset the stress. Well, the stress was that you added a reactant. That's going to push this to the product side again. So part B's answer is going to be pretty similar to that of part A's. Predict what will happen to the intensity of the blue. The blue color will become more intense. For very much the same reason. The addition of those chloride ions shifts the equilibrium to the product side, which again is more blue. Question 4 is a comparison of the reaction quotient Q versus the equilibrium constant K. We've got an equilibrium system here. Here's our reaction. At a certain moment, the pressures are calculated as such. The equilibrium constant at 500 Kelvin is 85. So this should be slightly product favored. Calculate the reaction quotient Q, and they're using QP because these are all gases. So the first thing we need to do is write out our reaction quotient expression. Since they're all gases, we'll use pressures. The pressure of SO3 will be squared due to the coefficient of 2 out front, divided by the pressure of SO2 squared times the pressure of the oxygen. And now we just need to plug in these values here. Because we're not sure we're at equilibrium, this will just represent our reaction quotient Q, in this case QP. Okay. The pressure of SO3 at this moment is 1.20, which is squared. The pressure of SO2 is 0.40, which is also squared. And the pressure of the oxygen is 0.60. So let's plug this into the calculator. And assuming I managed to plug that in correctly, I got a Q value of 15. Again, this has no unit. This is just like our equilibrium constant K. It has no unit. So that is the answer for part A. We have calculated the reaction quotient. Part B, predict the direction the reaction will shift to reach equilibrium, meaning left, right, or forward or reverse, or no shift. Actually, I said that incorrectly, didn't I? Left would be the reverse, right would be forward. Well, what we need to do here is compare Q to K. Q is 15, whereas K is 85. So that means Q is less than K. We do not have as many products yet as we would expect when we hit equilibrium. So since Q is less than K, this reaction will progress right or in the forward direction to reach equilibrium. The reaction will progress forward, which I'm going to match their terminology. They said right to reach equilibrium. Very important here that you make this official comparison of Q versus K. And our last question here is about some more gas equilibrium and pressures. We have a reaction. At equilibrium, we're given the partial pressure of the NO2 and the pressure of the N2O4. Part A, write the expression for Kp. Well, that's easy enough. Kp equals the pressure of the N2O4. That was a terrible parenthesis. Let's try it again. Divided by the pressure of the NO2, and that guy is going to be squared due to the coefficient of 2 out front. And there's your answer for A. For part B, calculate the value of the Kp here. Well, I need to calculate this value, which means I need equilibrium pressures of these guys. Well, those were provided in the prompt. So Kp equals the pressure of the N2O4, which is 0.60, divided by the pressure of the NO2, which is 0.30. But that 0.30 is squared. So we'll just plug this into our calculator. 0.6 divided by 0.3 squared. And that yields a K value of 2 sig figs, so 6.7. Part C, the reaction vessel is it's compressed to half its original volume while keeping the temperature constant. Predict whether the equilibrium will shift towards the reactants, the products, or remain unchanged, and justify using Le Chatelier's principle. Well, half the original volume means that you are doubling the pressure. So a doubling of the pressure, and since we're doubling the pressure, to offset that, this reaction should shift to the side with fewer moles of gas. In this case, you have 2 moles of gas versus 1 mole of gas. This reaction will shift to the right. So actually, let's match their terminology. Predict whether the equilibrium will shift towards the reactants or the products. This is going to shift towards the products. Shift towards products. And our justification was that an increase in pressure favors the side with fewer moles of gas, which in this case is the product side.